Good evening. Welcome once again to the live classes for preparations towards UTME, that is Jamb, WAEC, GC, NECO, or any other O-level exams you will be writing. In this class and subsequent classes, we will be delving into the subject of mathematics. Over the course of our classes, we would look at a whole host of topics, as well as how to answer those topics, as well as the core concepts that must be learnt for each of these topics. Under mathematics, the curriculum that guides mathematical studies in Nigeria, which is the NERDC, has splitted mathematics into some core topics. Now, these core topics can be identified under the branches of algebra, calculus, statistics, and of course, geometry. Every single topic that you will have at O-level and of course A-level mathematics will cut across these four major branches. Now we would identify and itemize some of the topics that we will be having over the course of the next few months. For October, our focus would be to introduce you to the concept of mathematics, as well as guide you towards the key steps that will be necessary for you towards learning the concept and the subject known as mathematics. In this lesson, we will be looking at core topics ranging from the basic indices, logarithms, indicial equations, logarithmic equations, sets, and of course, which is also known as set theory. We would also take sequences and series, which, as we would note, is more than just our APs and GPs, but also contains recurrences. We would, of course, discuss two-dimensional shapes. We will discuss three-dimensional shapes, which are usually called solid shapes, while the two-dimensional shapes are called plane shapes. Beyond this, we will consider trigonometry alongside a host of other topics. But this gives you an idea of where we'll be coming from. Now, the beauty about mathematics in any examination you'll be taking, whether it is Jamb, WAEC, GC, NECO, or any other kind of O-level or of course preliminary A-level exam, is that there is always going to be a guide in which you can follow through towards getting which courses or which topics will be essential for you to practice on. For instance, in objective-based examinations like Jamb, the emphasis would be on speed, as well as questions you would be able to solve in the shortest possible time, because it's objective-based. However, in examinations like the WAEC or the GCE, emphasis will be placed more on the theoretical parts of the examination. Why? Because the theory carries more marks than the objectives. In this case, the examiner is not just concerned towards you getting your answer, he also needs to know what steps or methods you want to use towards approaching these answers. These are very, very important tricks and strategies that we will be sharing with you over the course of these classes. Now, Let us start by picking out some of these important strategies. We'll start first and foremost from simple to complex. For instance, you will look at these first four topics that we have here: indices, logarithms, initial equations, and logarithmic equations. These four topics are in fact topics that are very, very interwoven and share distinct but similar characteristics from one another. We start first and foremost with indices and logarithms. First off, we will define indices blankly as expressions that have a base and a power. In the case of logarithms, we will define it as expressions where a log is written, and attached to this log, there is a number and a base. These are the two general representations that we have: indices, logarithms. Now, the very first, of course, they look distinct, which means they don't seem to have anything to do with one another. However, the biggest similarity that exists between indices and logarithms is the fact that an expression can be immediately converted from an initial look to a logarithmic look. How? Between indices and logarithms, there is a relationship expressed simply as a raised by x is equal to b. Now, this left-hand side is an initial representation equal to a number. Now, how does this link us to logarithms? Let's start by defining what this expression is. This expression is saying that the number b is equal to a raised to the power of x, which means if I were to multiply a with itself x times, I expect to get b. In practice, that means if I have 3 squared, I expect to get 9. If I have 5 cubed, I expect to get 125. Why? Because 3 squared is 3 times 3. That is 3 multiplying itself twice, while 5 cubed is 5 multiplying itself 3 times. So if I multiply a with itself x times, I expect to get b. However, I could rewrite this expression in terms of the logarithmic value. Why? Because if x is the power, I must raise a in order to get b, then x can also be written as the logarithm of b to base a. This is very, very important. And in fact, this relationship is now the connector to initial and logarithmic equations. So let's see. We say a raised by x is equal to b, whereby this x is in fact the logarithm of that number b to the base a. So what do you notice? The base in the indices, right, is also the base in the logarithm. That's the first key thing. The base in the indices is also the base in the logarithm, right? The power of the indices, right, is the result of the logarithm of that number to that base, right? So if I have a raised by x is equal to b, it simply means that x is equal to log b to the base of a. And this is very, very important. Because of this relationship, we can do so many things in indices, logarithms, and by extension, initial and logarithmic equations. In fact, if you have not noticed, this first expression is in fact an equation. Now, what is the difference between an expression and an equation? This is an expression. Why? Because you cannot see any equal to symbol in it, right? An expression becomes an equation when the equal to is added to it. So if I just write 3 squared, that's just an expression. That's a numeric expression. But the moment I say 3 squared is equal to 9, then it becomes an equation. So 3 squared alone, an expression. 3 squared is equal to 9 becomes an equation. Does that make sense? So this initial expression, right, when it is equated to anything, becomes an initial equation. Similarly, this logarithmic expression, when it is equated to something, becomes a logarithmic equation. So you see when I say these 4 topics have distinct identities but are very, very similar, you now see what it means. So what does that immediately tell you? That tells you that in mathematics, and of course, for all the classes we'll be having beyond today, every single concept is going to be linked one after the other, one after the other. There is no such thing as a concept that is independent of every other concept in O-level mathematics. No. What you learn in a topic is going to be useful in another topic. It might not be the topic that follows it, but it will definitely be useful in another topic. For instance, when we talk about the concept of quadratic equations, it's not in this list, but it's also something we'll be talking about very, very seriously. When we talk about the concept of quadratic equations, we talk about equations where the highest power is 2. You'll find out that later on, after learning about quadratic equations and you have left it for a long while, you get exposed to what we call polynomials, which are equations or expressions where the power can either be 1, 2, 3, 4, and so on and so forth. What it means is that quadratic equation is just like a small child inside the concept of polynomials. That gives you an idea of whatever you have learned in quadratic equations will definitely be very, very relevant when you tackle polynomials. Similarly, whatever you learn on indices, logarithms becomes very, very important when you decide to talk about initial equations and logarithmic equations. And that is not even just the end of it. There is one more concept that is related to these 4 that a lot of people don't even usually realize, and that is the concept of surds. Surds. Surds, of course, are expressions with a square root. And usually people will be like, surds, something's different entirely. There is nothing that looks like surds. However, what you don't immediately realize is that surd forms are simply a kind of indices, right? Everything you know about surds is just simple. It's just simply a kind of indices. It's just an offspring of indices. And we'll see why in a few minutes. Remember, we have said that indices is a base raised to a particular power. That is the representation that formulates indices, which means that this power could be anything and it will represent the amount of times that base is multiplied with itself or divided by itself, as the case might be. Now, it means that if you have a as the base raised to the power of x, where x can be anything, it means that x can also either be a normal number, that's a whole number, or it can be a negative whole number, or it can even be a fraction. Let's see what that means. If we say a squared, then that means we'll have a multiplied by a. That's a multiplied itself twice. If we say a is to the power 4, that is a multiplying itself 4 times. But then we can always say a raised to the power of -2. In this case, it's a negative power. So one of the rules or one of the laws of indices that we will still get to go in depth later on, once we start, we will still go into each of these topics and look at the general rules we have inside each of them. But for now, let us consider when we have a raised to the power minus 2. In this case, because there's a negative sign, the very first thing we do before we consider the number is to first remove that negative sign. In this case, we will have to express it as a fraction, which means whenever you have a negative of an indices, you first express that indices as a reciprocal, such that now you now see that the denominator is a squared, positive 1. And that immediately is like saying 1 divided by a times a. Right? You can do the same thing for a raised to the power minus 4 and so on and so forth. So what if we now have a raised to the power of 1 over 2? Now, in this case, the power is no longer negative, but it is in fact a fraction. What does the rules, or what do the rules of indices or the laws of indices guide us towards? In this case, whenever we have a fraction as a power, we use the numerator and the denominator of that fraction as a representative of the base. What does that mean? It means that we will use the numerator of the fraction as a power and use the denominator as a root. What does this mean? It means that if I have a raised to the power 1 over 2, it's the same thing as taking square root of a raised to the power of 1. Of course, a raised to the power 1 does not really change, but that's still a. But then it means that this would be square root of a. Now, this is very, very interesting. Most times, whenever we want to write the square root of a, we do not usually write the 2, right? Because we believe that whenever we talk about square roots, the 2, whether it's there or not, does not really matter. Which means I could write this as the square root of a without putting the number. So if you have the square root written this way without any number there, then it simply means that the number there is 2, which is why it's called square root. If the number was 3, it will be called cube root, because 3 represents the cube if it was represented as a power, and so on and so forth. But let's go back here. What it simply means is that if I have a raised to the power 1 over 2, that is simply the square root of a. But the square root of a is the representation of surds, right? Surds are mathematical concepts that can be represented in the form of a square root, right? In fact, the general form of surds is written as a plus square root of b, right? Whenever a square root is present in a representation or an expression, you call that expression a surd form. What does this immediately tell you? It tells you that the surd forms you are familiar with are just representations whenever that indicial expression has a power of 1 over 2. So that tells you how indices relates to surds. And because of this, it immediately means that every single concept you can do under indices will definitely work for surds, right? Because they are simply of the same family, right? So let's pick side by side and pick some little things and see that they are actually the same between indices and surds. Let's see. First off, for indices, we are told that if we multiply two indicial forms where the base is the same, but the power is different. Because we are multiplying, the final result will simply be an addition of the power, right? Because the base is the same, I can take one base and then add the power. The same thing holds for surds. Because in surds, if I have root A times root A, I'll just say my final answer is A, Abi? But then, why is my final answer A? That is because if I say root A, that is the same thing as A raised to power 1 over 2 times the second root A, that's also A raised to power 1 over 2. The base is the same, which means that I can add the power because of the law of indices. And if I add 1 over 2 to 1 over 2, that gives me 1. That is A raised to power 1. And A raised to power 1 is what? Is A. So you see that multiplication of surds still follow the same multiplication rule in indices, right? And if it is the power representation that you want to even check out, it even makes so much sense. For instance, in this case, if you have A raised to the power of m multiplied by B raised to the power of m in indices, this time around, the base is different, but the power is the same. In this case, we'll say that since the power is the same, we will take one unique power, right? And then multiply the base, because the operation there is multiplication. In this case, since the base is the same, the power is what we are after, so we will add the power, right? But in this case, the power is the same, the base is the one that we are after. So in this case, we multiply the base. Here we add the power, here we multiply the base, which means our result here will be A times B raised to the power m, or we write it as AB raised to the power m. It still holds true when we consider surd forms. If we have square root of 2 times square root of 3, our basic knowledge tells us that the answer to this is square root of 6. Why? Because we said 2 times 3. But what exactly have we done? What we have simply done is, because square root of 2 is 2 raised to the power half times square root of 3, that's 3 raised to the power half. The power is the same. So in this case, it means 2 times 3 raised to the power half, which is 6 raised to the power half. So this immediately, of course, you can try out other different expressions in indices and compare if it actually works for surds as well. Later on, we will take indices as a topic and consider all the 7 laws that guide indices, as well as also consider surds as a topic and consider conjugation and rationalizations as they hold true in surds. But that's not our focus today. As I've said earlier, the focus today is to show you exactly what we will be looking at in the course of mathematics and show you that they are simple concepts that you can easily get without any stress whatsoever. So let's proceed. The next thing that should come to our attention Great. Now, of course, it is not just these 4 topics that have something to do with one another, right? As I've said so many times, every single topic in mathematics is linked to at least one topic. right? Of course, they might not be linked as a